We're going to start by making a power series for this rational function, 2 over 4 minus 6x. And hopefully by now you're recognizing, oh, a rational function. That is the form that our infinite geometric series take, a1 over 1 minus r. With one small catch. We're going to have a lot of those today. That 4 is supposed to be a 1. It's supposed to be a1 over 1 minus r. No problem for us. We've seen this before. I can simply rewrite this as 2 over 4. If I divide everything by 4, 2 over 4 over 1 minus 6 over 4x. And now I've got my 1. I can identify the a1 of 1/2 and the r of 3/2 x. And I can turn this into a geometric series. So f of x is equal to the sum from n equals 0 to infinity of a1 times r to the n minus 1. Although I'm sorry, if I'm starting with n equals 0, I don't need the minus 1 there. So 1/2 times r to the nth. That is my Taylor series. Fantastic. But there's a catch. That's my f of x. If I look at the graph of this to see if this actually holds up, here's the graph of 2 over 4 minus 6x. And here is my Taylor series. I'll turn that on so we can see it. And you can see, at least with two terms, you can see my a, this slider right here, is the number of terms. If I look at just the first two terms, I'm sorry, you can't see the whole bunch right now, but you can see the graph. If I add the number of terms here, you can see the more terms I add, the closer it gets. You can see I'm adding more and more terms here. But there's a limit here. No matter how many terms I add, it's never going to be a very good prediction over here. Down here, it's still not a good prediction. If I add another term, it doesn't get better. It just switches to up here. So we've seen this before. There's only so many values for x where this blue prediction of the red curve actually works. It's like very, very good when it's good. But then all of a sudden, it becomes very, very not so good. The question is, when does that become not so good? And we saw this in our last class and a couple of classes last week. Also, that's called the interval of convergence. When is the graph good? Well, luckily, we know when this graph is good because it is a geometric series. And we know that a geometric series is only good because the formula a1 over 1 minus r actually only applies to a geometric series only if the absolute value of r is less than 1. Well, we know what r is. It's 3/2 x. So we need the absolute value of 3/2 x to be less than 1, which means 3/2 x needs to be between -1 and 1. Because if you remember, absolute values become compound inequalities. This one becomes an and inequality. And we can solve this one without too much trouble. Multiply everything by 2. And then divide everything by 3. So as long as x is between -2/3 and 2/3, this should be a good fit. If we go back to our graph here, and if I put those numbers back on, you can see that that's true. This is right over here. This is where x is -2/3. And we can see we're going to follow this asymptote all the way up to where x is positive 2/3 also. And you can see as we get closer and closer to x is 2/3, we're still following. And it's really only when we get incredibly close that we pull away. But you might be asking the question, what about all of our other Taylor series? What about all the other times, like e to the x and cosine of x and sine of x and ln of x and all the others that we built where the Taylor series wasn't just a geometric series. Well, what do we do when there's no r to speak of? Well, the answer might please you, is we basically just pretend there is an r. If there is no common ratio, if it's not a geometric series, what we're going to do is look at the limit of the ratios and pretend that's the common ratio, and we will check and see if that limit, which is just as good as the common ratio as far as we're concerned, if the absolute value of that is less than 1. So we're going to take, reading from left to right here, we're going to find this ratio. We can't just call it plain old r, because that implies that the ratio is the same for every pair of terms. So we use this notation r sub n to mean r, the ratio between the nth term and the next term after it, is the ratio of any term, a sub n plus 1, divided by the term before it, a sub n. And what we're going to do is take the limit of that. That's what we'll call L for limit. We'll take the limit of that as we get to the infinite term. So we're looking for the limit of the ratio of any term divided by the term before it as we move farther down the list of terms. And this is where, and it ends up being not as complicated as it looks right now. This is where the geometric series becomes very useful, because once we have that limit, we can kind of think of it the same way as a geometric series. As long as that limit is less than 1, the series will converge. And whenever that limit is greater than 1, the series will diverge. Just like the geometric series, it only matters whether r is bigger than or less than 1. And remember that L is going to be in terms of x, usually, because this ratio over here, all those terms, if we're talking about a power series, those terms are in terms of x, which means that the limit is going to be in terms of x. So what we're doing here is we're finding for which x values will L be less than 1, or will L be greater than 1. You might have noticed that there's something missing from that pair of statements. If L is less than 1, the series will converge. If L is greater than 1, the series will diverge. That's the basics of the ratio test. You might be asking, well, what about when L equals 1? And the answer to that is not today. We will talk about that when L equals 1. You've got more work to do. We're not going to do it today, but hey, it's something to look forward to for next class. So we will use this idea to find the interval of convergence for one of our series that is not geometric. We'll do it for the Taylor series for ln of x. So in order to do that, we need to remember what the Taylor series for ln of x is. So hopefully we have that one. ln of x is equal to, well, it's x minus 1 minus x minus 1 squared over 2 plus x minus 1 cubed over 3. So it's like all of the others, except instead of switching off odd and even exponents and factor and denominators, it's all of the numbers, kind of like e to the x. But like sine and cosine, the terms are alternating signs, that is, plus, negative, plus, negative. And unlike any of those, the denominators are all constant, are all simple numbers, not factorials. So we'll kind of put all that together and say that this is the sum from n equals 1 to infinity of negative 1 to the n plus 1. That's how we alternate, starting with a positive, times x minus 1 to the nth over n. Which means that the ratio of any term, remember, the ratio of any two terms is equal to any term, or the next term divided by the term before it. So what I'm going to do there is fill in n plus 1. Well, here, I'll show you how it looks. So the next term would be, so a sub n plus 1 would be if I take this n and I replace it with n plus 1. That's how we can write the next term. So I'm going to put an n plus 1 in my exponent, but it's n plus 1 plus 1, because that plus 1 is there too. So I'm going to write that as n plus 2. And if this doesn't make sense to you quite yet, that's okay. First of all, it will in a minute. Second of all, this negative 1 doesn't even matter in the end, because we're going to take the absolute value in a minute. Times x minus 1. And then instead of n here, it's n plus 1, because we're talking about the next term, divided by n plus 1. Because again, this n, we're talking about the next term, so we'll divide by n plus 1. So far I've done that part. Now I need to divide that by a sub n. Now, because every term is going to be this fraction, I'm going to find that it's a lot simpler to write, instead of dividing by a sub n, I'm going to multiply by the reciprocal of a sub n, which just means take the reciprocal of that, n over negative 1 to the n plus 1 times x minus 1 to the nth. And so this is my ratio. What we can do is simplify this. We can't simplify all of it, but the x minus 1 over n plus 1 over x minus 1 to the nth. So if we look at these two factors, that cancels out. Like, imagine if that wasn't an x minus 1, if it was something a little easier, like a 5. What we'd be looking at is like 5 to the 12th over 5 to the 11th. Or 5 to the 73rd over 5 to the 72nd. Or 5 to the 150th over 5 to the 149th. Because whatever term we're at, whatever this n is, n plus 1 is just one more 5. Or in this case, it's one more x minus 1. So x minus 1 to the n plus 1 over x minus 1 to the nth will just be x minus 1. The n over n plus 1 we can't exactly cancel out. You can't reduce that. We know that. And the negative 1 to the n plus 2 over negative 1 to the n plus 1. Well, if we have like negative 1 to the 50th, that's positive, and negative 1 to the 49th, that's negative. Well, you're always going to have a negative over a positive, or a positive or a negative. So it's always just going to be a negative. That's our ratio of the nth terms. But remember, what we care about is the limit of those, really the limit of the absolute value of those, so I'm going to ignore that negative. So that's our next step, is to take the limit of the ratio. So see what we've done here. First we found the ratio of consecutive terms, and then we're taking the limit of this ratio, really the absolute value of that ratio, as we get towards the far end terms, as we get to an infinite level of terms. So in this case, we can plug in what we just found for the r sub n is negative 1 times x minus 1 times n over n plus 1. And this is where I can just completely ignore that negative because it's inside an absolute value. So if you want to just not write it here to begin with, that's fine. And as we learned with limits way back earlier in the year, when we've got the limit of a product, we can separate that into two different limits. So I can pull out the limit as n approaches infinity of everything with an n in it. And I'm going to separate that from the other factor, the limit as n approaches infinity, of everything that doesn't have an n in it, which is just x minus 1. Well, this is something we know from Algebra 2. The limit as n approaches infinity of n over n plus 1. N over n plus 1 is just a rational expression, which as the input gets bigger and bigger and bigger, would approach its horizontal asymptote. And the horizontal asymptote of that is 1. Remember, it's n over n. We look at just those lead terms. So this whole thing is just 1. And the limit as n approaches infinity of x minus 1, well, the limit of something that doesn't have an n in it as n approaches infinity is just x minus 1. So my L is just equal to x minus 1, really the absolute value of x minus 1. We still do have that here. We're able to ignore it around the negative 1, but we can't ignore it everywhere. And so our L is equal to the absolute value of x minus 1. And what we've said is this series will converge as long as that L is less than 1. So this is our interval of convergence. As long as x, the absolute value of x minus 1 is less than 1, which means x minus 1 has to be between -1 and 1, which means if we add 1 everywhere, x itself has to be between 0 and 2. As long as x is between 0 and 2, our series will converge, which is a fancy way of saying that our power series will actually equal ln of x. So that's our interval of convergence. The radius of convergence is just half the width of the interval. Which, if the interval goes from 0 to 2, half of that width is 1. So the radius of convergence is 1. And if we kind of imagine what the graph of the ln of x looks like this. That's the ln of x. And our power series, if we were to graph our power series, it would follow the curve very, very well until it gets close to 2. And that's when our power series would turn off course.